Hi friends, in this video we'll discuss about hydrogen storage in an activated carbon. So what you can see here, it's a tank in which there is an activated carbon present. So you can say here this is an activated carbon, and this activated carbon is also a porous media, right? So in the porous media there is an activated carbon. So it is here there is a carbon present, and accordingly here there is a carbon present, and there is a gap between this carbon particles or carbon porous media, so into which we are flowing the hydrogen. So the hydrogen will enter here, and at this interface it starts compressing, and when it enters into this activated carbon porous media, it starts depositing on the carbon. So that is the way how we will store energy or store the hydrogen onto the activated carbon, and accordingly when we want we'll release that hydrogen again from the activated carbon. So now we will try to replicate the process of hydrogen adsorption onto the activated carbon through ANSYS fluent in this video. So what you can see is the continuity equation, momentum equation, and energy equation when the hydrogen enters into the activated carbon, and this is the porous PCM phase change material. So when the when the hydrogen adsorbs onto the carbon, it releases the heat, and that heat will be stored or will be dissipated into the surroundings, and here the surroundings is the phase change material into which we reduce the heat, and between the phase change material and this hydrogen activated carbon there is a thin layer of stainless steel. This is steel layer, right? This is a steel layer. So once when this hydrogen enters into this activated carbon, so there is energy that will be dissipated, and that dissipated energy will be traveling through this phase change material, and it will be stored in the phase change material. So now when the activated carbon is being exposed to the hydrogen, it starts depositing, or the hydrogen starts depositing in the activated carbon, and now the porosity of the carbon will tries to decrease. Now the because the hydrogen is been adsorbed, and the porosity will decrease, as well as the specific heat capacity Cp is no more a Cp of carbon, it is a Cp of hydrogen plus carbon. So you can see here this is the specific heat capacity, which is dependent on solid carbon plus the gaseous form of that hydrogen which is been depositing onto the carbon. So this is the equation what we'll try to use in the ANSYS fluent for the specific heat capacity. And now once the hydrogen comes here onto the carbon at a certain temperature and pressure, the hydrogen starts adsorbing onto the carbon. So the pressure and the temperature at which it starts adsorbing onto the carbon is this. So you can see here dN by dt. dN by dt is the rate of deposition of hydrogen onto the carbon. It depends on N star as well as N. N is the initial amount of hydrogen that is present in the carbon. Initially there is no hydrogen, so initial conditions will take N as 0, but as this depends on N star, where N star is again a function of temperature and pressure, right? And P naught is a saturated pressure. So P naught is a saturated pressure above which there will be no adsorption, right? So now once the hydrogen enters here, the temperature of the hydrogen increases due to the accumulation, as well as the pressure also increases. When the temperature and pressure increases, the amount of hydrogen getting adsorbed onto the carbon also increases up to certain extent. So that is called adsorption isotherm. It will be in this way. So the adsorption increases up to this point. After that it will remain constant. Even though increase the temperature and pressure, there will be no adsorption that will occur onto the carbon. So now the adsorption will dependent on the temperature and the pressure of the hydrogen that is present in the activated carbon porous media, right? So rate of adsorption onto the carbon is equals to K into N star minus N. So it is K into N star minus N. And what is the value of K, what is the value of N star, everything I'll just show you meanwhile. So this is the rate at which the hydrogen starts adsorbing onto the carbon. Once this has been absorbed onto the carbon, the hydrogen content will decrease, right? So decrease in hydrogen mass fraction is given in the continuity equation using this. So it depends on the rate at which the hydrogen is being deposited onto the carbon. So obviously rate at which if it is deposited to the carbon, the hydrogen content also reduces. That reduction is given through this equation, and there is a porosity of this hydrogen present inside the carbon. So the porosity effects are also taken using the momentum equation, and it releases some energy as it is being deposited. So that energy also is taken care using this equation source term, which is Sc equals to minus delta H Sm by molecular weight of hydrogen. Sm is nothing but the mass of the hydrogen that is being deposited onto the carbon, that is this one. So this entire term is Sm. So that Sm is being used in the energy equation to find the source term, that is the heat generated due to the adsorption of hydrogen onto the carbon. Okay, so that source term has been added here in the energy equation of the hydrogen. So now we will just go through the ANSYS Fluent tool, how to add all these source terms into the hydrogen, so to simulate the hydrogen storage process in an activated carbon. Okay, so now just activate the transient, and gravity is in minus 9.81. right? Go to models. So this will be laminar flow. Okay, on the solidification and melting also. Okay, go to materials. We'll try to create two materials. One is for hydrogen, other is for PCM. So go to materials, just go to Fluent database. Get the hydrogen. We'll try to change the A to PCM. The properties, everything is present here. You can just check the PCM. So density will be taking as 760. This will take assumed as a bosonic approximation with 760, and coefficient of thermal expansion I will be taking as 0.01. Solvent heat is, you can just check these properties. Latent heat is 190. Sorry, it is not 170. Solid melting heat is 293.15 and 296.15. So before the solidus temperature, it will be in the solid format. During the solidus temperature to liquidus temperature, it will be in the semi-solid and the liquid format. After the liquidus temperature, it will be in the complete liquid format. The viscosity is given as 0.02. Thermal conductivity is 0.2. Thermal conductivity is 0.2. And the specific heat 2000. This will name it as PCM. Change create. Yes, overwrite. Also try to get the stainless steel material. Get the steel. The cell zone condition in the fluid for the PCM. Try to apply the PCM material, it is already applied. And for the bottom fluid, it is hydrogen with porous zone. So this is the bottom fluid. What you can see is the bottom fluid here. I'll just highlight it, you'll understand. This part is bottom fluid, and this part is entry fluid, and this part is top fluid. Okay. So for the bottom fluid, it is a porous zone where there is an activated carbon onto which hydrogen will get adsorbed. The properties, so the direction vector is 0 and 1. Sorry, it is 1 only, it's correct. So viscous resistance, inertial resistances we'll take from here. Activated carbon, the hydrogen viscous resistance is 829055 into 10 power 7. 8290 p power 7. Just verify again. So it's 8.290. Sorry, 8.290. And inertial resistance is given as 7586. These are the properties what we'll get from Darcy's equation for the inertial and viscous resistances. Okay. And the material is carbon, so we'll just forgot we also need to get the carbon properties. So we'll just change the aluminum to carbon and we'll assign the properties to that carbon. Cv, density of the carbon here, it is given as density is a 517.6. Specific heat is 825. In thermal conductivity is 0.646. Change rate, yes. The bottom fluid, that is carbon, and the porosity is given as 0.46. This is 0.49, sorry. And there is a source terms for these hydrogen that we are taking here, because here the mass will be adsorbed onto the reactant or the reacted carbon. So I'll just show you the UDF what we are using for this. So this is the UDF what we are trying to use, right, in which we are trying to calculate the rate at which the hydrogen starts adsorbing, which is dependent on the N star and the individual or entry level hydrogen that is present on the carbon. So that is given by user defined scalar. So we first need to activate the user defined scalar. Go to user defined scalars. I'm using one user defined scalar, and here we are trying to use it on the selected zone only, that is bottom fluid. Okay, and the mass function default, and we'll use the default unsteady function. Click OK. And the user defined memories, I'm using 3 memories for my convenience for the usage in order to use it and save it and use in the source terms. So you can see here, once we are calculating the n rate is nothing but dn by dt, what I have already shown you here, this dn by dt, which is k into n star minus n. So k into n star minus n, here KLH2, which is taken as this 0.45 from the publication, and 0.45 into n star we are calculating using this formula what I have already given in here. This is the formula for n star, what you are seeing on the screen. This is the formula for n star, and the n is the initial patching what we will do, that is initially it is 0. So after there on it will be calculated, and we are trying to store that in the user defined memory n rate, and we are trying to supply it to the source terms in order to remove the mass from the hydrogen which is been created. Okay, so this is the source term that has been getting removed. You can just check here what we are removing is the source term minus 1 minus porosity into density of particles into molecular weight into dou n by dou t. So that is the term what we are removing here, C underscore UDMA, which is dou n by dou t, 1 minus epsilon into molecular weight of hydrogen into rho naught. Similarly, energy term also we are trying to remove in the same fashion what you can see in the screen here, Sc equals to minus delta H Sm into m by H2, right? So the same term we are removing here using the user defined memory which is allocated and we are removing that source term, and we are trying to save it in the user defined memory C comma T comma 2. Okay, so now we will try to compile and load that UDF first. So we got those. So we'll try to execute it, and first for each and every time step we are trying to calculate these values C underscore UDMI and trying to use them in the individual mass source term as well as energy source term to add the energy as well as to remove the mass from the hydrogen gas in the bottom part of the fluid. So now go to the bottom part of the fluid, and in the source terms, mass source term, we need to remove that hydrogen which is being adsorbed onto the carbon. So this is the mass source term, click apply, and we need to remove the energy source term or the add the energy source term which will be creating extra energy when it is adsorbed onto the carbon, and that energy will be stored inside the porous and will be transferred to the phase change material from porous to the phase change material through steel. Okay, close it, and we'll give the mass flow rate to this inlet, mass flow inlet with 0. kg per second, the initial temperature of 293 Kelvin. We'll be giving it with 300 Kelvin, that will be okay. Okay, remaining all parts are filled with hydrogen only. We'll just verify it. So this should be hydrogen, not PCM. Top fluid should also be with hydrogen, and the liner will be with steel, so that also will verify. This is also with hydrogen, it's okay. With the part steel or a thin liner, what is present should be with steel. What I have shown on the screen, this part should be with steel, that has been given here with steel. So you have taken here. Now we'll just initialize. When you're initializing, user defined scalar should be with 0, and also verify we are using the 4 memory user defined memories, so the count should also be greater than 3 in order to avoid any crashing due to the segmentation violation. So we'll just, it's taking time to load. It got loaded. Verify the memories, increase it, initialize. It's taking time for initialization. So we'll also have the graphics in order to have the temperature variations with respect to time. So we'll go to graphics, create a counter with the temperature, how it is varying with respect to time. We'll just extract the animation and I'll show you after running the calculation. So I'll try to take 0.1 as my time step size, and with 5000 we'll increase the number of time steps and click on calculate. So now after running through many time steps and adjusting, so you can just check how the temperature is present. Just show you the temperature. So velocity magnitude. So this is how the temperature is varying. The temperature has been getting more at the center part. You can just check how the temperature is getting more at the center part. Maybe I'll create this. This is the way how it looks like when you have the 310 Kelvin as when upper limit. So it is getting deposited. More and more temperature is being liberated at this porous media, and the temperature that is being liberated, or the heat that is liberated, is transferring to the adjacent PCM phase change materials. I'll just activate only the phase change material, then you'll be understanding more how the energy is being transferred to the phase change material. You can see more amount of heat is transferred to the phase change materials here, and it is again increasing here also. In this phase regions, the phase change material is turning into the liquid format. And you can also check the velocities, how they are been varying inside the phase change material. You can see more velocities are formed here, as well as you can just check in the bottom part of the fluid how the velocities are getting distributed. Here the velocities are in this way. If you can decrease that, you can just see there is more velocities present here, the top part. At the bottom part the velocities are low, but it is been reduced. And I'll just show you the animation how exactly I've saved all these steps. Maybe I have extracted an animation. I'll just show it to you how the temperatures are being varying from the initial time. You can just see. So all the temperatures, as you can see, the heat is been getting deposited at the center part of the activated carbon, and that heat is been again transferred to the phase change material. So this is the temperature variation, and I will also show you the amount of hydrogen that is being deposited into the carbon. So this is a user defined scalar, this one. So you can see more amount of hydrogen is being getting transferred, and when it is transferred it is getting deposited onto the carbon, and at the edges you can just check how it has been more in nature compared to the center point. You can see hydrogen is being deposited into the carbon. The gradient is, or the more is present on the edges or the interface, but yes, nonetheless it is same in the region in the center also. There's a more amount of hydrogen that is being stored at the carbon in the center location also. So yeah, this helps in understanding how the hydrogen is being stored inside an activated hydrocarbon, and the energy is released due to the storage. And this is where how you can use the hydrogen storage devices in any of the automobile industry or any of the aeronautical or anywhere where you want to store the hydrogen. And yeah, please do subscribe the video and share it among your friends. Thank you.